It's time for another math easy solution. We're going to discuss the some examples using the second derivative test, basically illustrated. Further, I showed my earlier video, I introduced what second derivative test was, and now let's look at some examples. But to recap, basically, the second derivative is if you have, let's say, just a function like this here, where this is fx and this is, let's say, c, where you have, let's say, at c you have f of c is equal to 0. So then if you have this, and then if you have f double prime of x, say near c, is greater than 0, I'll just rewrote it there. But so basically if you have f double prime of x greater than 0 near c, like around here or whatnot, then you're going to get a local, this one's going to be a local minimum, and similarly this is concave upwards. And vice versa, I'll just write that down. If you have it the other way around, where you have, if you have f double prime of x is less than 0, then you're just gonna have a local maximum. And once again, this is near c, and this is also gonna be concave downwards. This is gonna be this opposite of that. So yeah, you can see my other video on basically illustrating this further, but now let's look at some examples here. Let's go with example 1. So example 1 states basically sketch this equation, y equals x to the 4 minus 4x cubed, and determine concavity, inflection points, local maximum wherever they occur. So basically, to start off with, we have to take the derivative. First, let's just write the equation down up here, minus 4x cubed. Then the first derivative is just going to be equal to, this is using power rule, 4x cubed minus 12x squared. You can simplify this further by taking the common values out, basically 4x squared out. And then you're going to have, this is going to be an x minus 3. And then similarly, the second derivative is going to be, this one's going to be using power rule here, just using 12x squared minus 24x. And again, you could simplify this one out by taking the common numbers out. 12x is common amongst these two terms, so we're going to have x minus 2. So now the first thing to do to basically to illustrate second derivative test, first we always have to find the critical points here. And the critical points is basically when you have when first derivative is equal to 0 and wherever x is those values. So basically when the first derivative is 0, we have to find what x is. And in this case, it's going to be 4x squared, x minus 3. And this function is going to be equal to 0 whenever, basically at 2 points here, when x is 0 and when x is 3. So we're going to have x is, and x equals to 3 here. And these are our critical points. Now, from this, we could basically apply our second derivative test here right now to basically determine local max or min here. So we know that at the critical points, this is because remember what I showed up here is basically when f of c is equal to 0. This is a critical point here. Yeah, so that's a critical point. So we have 2 already here. So we just have to find out what the second derivative is of both of these. So then we're going to have y double prime of 0. This one, if we plug it in to this equation here, well, this one's going to be 0 times, well, yeah, we're going to have 0 here. So it's going to be 12, 0. So this one's actually, well, 12 times 0, 0 minus 2. This just equals to 0. But then the second derivative test doesn't, we can't tell if it's local min or max because this one is 0 here and it's not greater or less than 0, so we can't tell. So we can't tell it there, but then so this doesn't, we can't apply a second derivative test at this critical point, so we don't have anything here. So there's no local max or min there. Actually, we can't tell if it is. I'll just erase that. So now let's look at the second critical point. So at x equals to 3, we know that the second derivative is going to be equal to 12, 3 times basically here, 3 minus 2. Well, this one is just 12 times 3 is 36, 3 times 2 is 1, so we're just going to have 36 here. And this one is greater than 0, so we could assume that near x's So it's right near x equals to 3. The second derivative is going to be greater than 0, so anywhere close to it. So then this one should be, as I showed above, here as I stated here, if it's x is greater than 0, then this is the local minimum. So then we could just write down this is local minimum here. And at the first critical point, we don't know what it is. So now the second thing to do is actually find possible inflection points. So we can just write that down. Basically, I showed my other video, inflection points are just where the second derivative changes from either less than 0 to greater than 0 or greater than 0 to less than 0. So we have to find out when it's equal to 0. So at f prime of 0 is equal to 0, we're going to have, basically we're going to have is equal to 12x. This one's x minus 2. So it's basically at possible inflection points are at x equals to 0 and x equals to 2 here. So now if we just draw a line across showing all of our critical numbers here. I just drew it a bit better here. So now we know that this is our critical point at x equals 0 and is also a possible inflection point. Let's go 1, 2. Let's draw this one here. This is at x equals to 2. Possible inflection point there. And then we have at x equals to 3 here is our critical point. So now we have to look at intervals of less than, is basically we look at every interval that's of interest here. So we're going to look at here, at this case, at x is less than 0. And then in between these two here, where x is less than 2, greater than 0. And then between these two right here, this one is x is less than 3, greater than 2. And then the last one, x is greater than 3. So we have to look at the second derivative and basically the first derivative at every interval. Yeah, so before we do that, let's just plug in what our function would be at the critical points. So y of 0 here is just equal to, well, this one's going to be 0, 4 minus 4 times 0 cubed. This just equals to 0. And then our other critical one, somewhat critical, is where possible inflection point, y of 2. This one's just going to be equals to 2, 4, minus 4, 2, 3. And taking the common number out just to simplify our calculation manually, just take 2 to 3 out. So we're going to have 2 to the 1 minus 4. This just equals to 8 times negative 2. And this equals to negative 16. And then our final critical number here, actually this is a 2 here, not a 0. Yeah, this just equals, so y of 3, this just equals to 3, 4 minus 4, 3, 3. Again, we could just take out the common numbers here, which is 3 to the power of 3. This equals to 3 to the power of 1 minus 4. This equals to 3 to 3 is 27 times negative 1. This equals to negative 27. So these 2 points right here, if we draw this one out all the way down to here, let's say this is negative 27, so this is 3, negative 27. And this possible inflection point is at, let's say, 16. This is 2, negative 16. And this is a 0, 0 here, we have a point there. So now if we make a little quick table here, let's say at interval here could be one of the columns. Interval of x is less than 0 here, then for basically y prime is equal to 4x cubed minus 12x squared here. See, I just rewrote that one, just write it in this way, 4x squared x minus 3, and then y prime here is y double prime at 12x minus x minus 2. So when it's less than 0 here, we know that this 4x it's always going to be positive here, and then this one's always going to be multiple. Yes, always going to be positive, and then if it's less than 0 here, this part's going to be a negative. So we're going to have a positive number times a negative number. So we're going to have a negative, derivative here. And then similarly, yeah. So if it's negative, it just means it's going to be going downwards. And then to see the concavity, we just look at this one here. Basically, if you put in negative, and this one's going to be negative here. And negative in x minus 2, it's also always going to be negative. So negative times a negative is going to be a positive. And I showed that a positive number is just concave upwards. So this was concave upward. So we could actually just draw that out here. If it's concave upward, it's going to be something like this. Where it's less than 0, it's going to be concaving up. And then now if we look at between 0 and 2 here, so x is less than, well, x is less than 2, greater than 0 here. If we plug this one in here, this is going to be a positive on the 4x. X minus 3, this one, it's going to be negative as well here, because it's less than 3 there, so we're going to have negative, so it just means the derivative is negative, so it's going to always go downwards. If we look at this one here, this one here is going to be positive actually between that, and this one's less than 2, so it's going to be a negative here. And it's going to be a negative, so this is concave upwards. And then from our second derivative test, we couldn't tell when this is 0, when f double prime is 0, if it was concave up or down, and then in this case there is neither of them, because it's concave downwards all the way until this where it becomes 0, and then it should be concave upwards now. So this is for less than 3, greater than 2. So between these two, this one's going to be positive again, this 4x squared, and this one's going to be negative because it's less than 3, so we're going to still keep going downwards because the derivative is that. And this one, 12x, is positive, and then this is greater than 2, so this will be positive as well, so we're going to have positive, and this is concave upwards. So we could just draw that out here. It's concave upwards, so this is where it changes, and it never changes again. There's no other inflection point here, so it's going to keep going like this forever. You could also plug that in here. Let's go where x is greater than 3. It's going to be positive, this is going to be positive, it's going to be increasing positive, and then this one is greater than it, so we're going to have positive, positive. Positive keeps going concave upwards. So it should look something like this. This one just keeps going straight up. Keep going straight up. You can put it also in Google, show it right now. Okay, so if we just type this in here, x to the 4 minus 3 times, 4 times x to the 3. Let's just see how this looks. Yeah, and this, as you can see, this graph looks just like the one I just made earlier. So let's just zoom this out a bit, out there. Yeah, so it looks something like this here. So we have the inflection point here. There's no local max here. This is, or local min. There's a local min right here where x or y is negative 27. Is that x equals 3? And as you see, it goes upwards forever, and it looks just like our curve right here. It looks just like this. Well, that's all for today. I was gonna do another example, but this video is getting pretty long. Maybe do it in another video. But that's all for today. Hopefully you learned. Basically, when you're doing second derivative test, you always have to put this in a table, kind of look at each interval, or once you get the hang of it, you'll see that if this is an inflection point, it should change. Anyways, you could also verify it by plugging these numbers here, and also remember that if second derivative is equal to 0, you can't tell if it's local max or min. In this case, there was neither. Just to further illustrate it. And if you were to find local maximum, you could also use the first derivative test, which might be easier using, and you can see that in my other video. That's all for today. Hopefully you learned, and stay tuned for another math easy solution.